And let me share my screen. Okay. So last time we learned quite a bit about continuity. We learned a characterization of continuity in terms of open sets. Yeah. So let's recall a map, a function f between two metric spaces x and y is said to be continuous on f if and only if for every open set u in y, the inverse of u under f, that's the pullback of u under f, is an open set in X, right? We saw an example, a non-example, right? We worked out the proof, and so then we looked at some corollaries of this theorem. The first one was, suppose that f is a function from x to y. Suppose that x is compact and f is continuous, then the image f of x is also compact, right? We provided a proof to this corollary, and we looked at another corollary which says that if there is a continuous function between two metric spaces, with the additional property that x is compact and this continuous function is actually a bijection. Yeah, so the map that we started off with is actually 1 1 and onto its image. Then we can talk about the inverse, right? The inverse is defined. F inverse is a map from y to x, and the point of this corollary is to show that the inverse map is also continuous, right? So last time I tried to sort of impress upon you that this is not straightforward. You know, whenever the inverse is defined, it need not be continuous, right? So we saw two examples to this effect. So is this bit okay, or do you have some questions from last time? No, yes, is that okay? So no means you don't have any other questions. So everything is fine, whatever we did last time. So we continue from that point. So which means that the first thing that we do today is to provide a proof to corollary 2. Is that correct? Yes. So let me write down that somewhere. Okay. So we are in lecture 22. Yeah, so we are going to look at the proof of corollary 2. Yeah, but before that, let's just quickly recall the statement one more time. What is that we are given and what is that we are required to prove? Yeah. So here is the statement. Yeah. X and y are metric spaces. F is a function from x into y. F by assumption is continuous, 1 1 and onto. X is compact, and we are required to show that the inverse map is also continuous, right? So given f from x to y, a continuous bijection, right? So it is 1 1 and onto map, a continuous bijection from a compact metric space X onto Y, right? We are required to show that the inverse map, which is defined now. Why is the inverse map defined? The inverse map, see, defining the inverse map is not a problem as long as the function f is given to be 1 1 and onto, right? What is the content of this corollary? The content is that the inverse map is continuous. Yeah. So let's let's write that down. We will show that f inverse from y onto x is a continuous function. Yeah, is that okay? Right.
Ma'am, I just have one doubt in this.
Yeah, go ahead.
Ma'am, for this entire corollary to hold, both x and y, both these metric spaces have to be compact, or just x has to be compact?
See, x, by assumption, x is only compact, but we already know that, right? The corollary one says that, so let's go back. So by assumption, only x is compact, but corollary one says what? The corollary one says, let's go back to that. Let's go back to the statement. Corollary one says that continuous image of a compact set is always compact, right?
Yes, ma'am.
Yes, is that okay, Priyanshu? So in this
Yes.
case, since the function f in the setting of corollary 2, since the function f is onto, the image is actually whole of y.
Okay, okay. Yes,
Right?
ma'am.
So y is compact follows as a consequence. You are
Okay.
not required to assume it.
Yes,
Yeah?
ma'am.
Let me go back to the statement one more time. Here it is. Yeah. So compactness of y is something which follows as a consequence. Assumption is only that x is compact. Yeah? The fact that f is continuous and x is compact implies that the image of f image of x under f is compact, and since f is onto in this case, that would imply that y is compact. Yeah, is that okay?
Yes, ma'am.
Yeah, all right. Anything else?
No, ma'am.
Oh, excellent. So let's look at how do we go about showing that the inverse function is, let me just clarify that this is the inverse function. Yeah, the inverse function is continuous. So what we will do is we will use the characterization of continuous functions in terms of open sets. Yeah, which means that the first theorem that we did last time, which said that let me just recall that theorem over here. Yeah, so I'm going to look at this theorem. Yeah, so so what does it say? In order to show that f is continuous on x, it's enough to show that for every open set u in y, the pullback of u under f is open in x. Yeah, we are going to apply this theorem to show that f of inverse is continuous function, right? Is that okay? So the first thing that I'm going to note is the following. Yeah. So let's start with, so I'm going to start with an open subset of x here, right? So I will note that. So the first thing is I make the following claim. So in order to show that the inverse function is continuous, it suffices to show that, so let me sort of write in this manner, right? So I need to pick up an open set of x and I will claim that. So let's see. So let me write it in this manner. Let G be an open subset of x. So in order to show that the inverse function is continuous, what are we required to show? We must show that you look at the function f, yeah, and its pullback under G, yeah. So you are looking at f inverse and pull it back, yeah. This is open in Y, right? So let's look at this. I have a function from Y to X. Call it G if you feel that is more comfortable. You look at G, which is open in X, and you pull it back via F inverse or G, and you get a set G inverse of G. Yeah, so this is F inverse inverse G. This is a subset of Y. You are required to show that this is open in Y. Is that okay? Is everybody with me on this? Is that a yes with everybody present here?
Yes, ma'am.
Yes, is that a yes? Excellent. All right. But you know, since f is given to be a bijection, yeah, f is 1, 1 and onto, what can you say about this set f inverse inverse G? What is this set? So I have G, which is a subset of X. I apply the map f inverse to it. So my question is the following. Since f is a bijection, f is 1, 1 and onto, what can you say about this set f inverse of G?
Ma'am, that should be equal to FG, I guess.
That's exactly equal to f of G. Yeah, thank you, Priyanshu. Yeah, it follows this set is exactly f of G. Is everybody with me up till this point? Is that a yes with everybody?
Yes, ma'am.
Yes. See, what is this double inverse says? You look at this set G. The first inverse says I am going to pull back the set G via the map F inverse, and that's how you get it. Okay. Okay. So let's recall, what are we required to show? We are required to, you start with G, open subset of X. You will show that F of G is open in Y, right? Okay. So how do we do this? So recall, I'll just sort of remind ourselves, recall that we need to show that f of G is open in Y, right? F of G is an open subset of Y. This is what we need to show. This is what we are trying to do. Okay. And what is it we are given? We are given that G is an open subset of X and X is compact, F is continuous and things like that. Okay. And you know, so X is here, F is here, and G is here, right? G is a subset of X. So let's look at the set X minus G. Yeah, the complement of G in the set X. Now G is an open subset of X. Then what does it say about the complement of G? It says that the complement of G is closed in X. Correct? Yes, so let's record this. Now the complement of G is closed in X and X is compact. So what happens? What is the next statement that I can say?
X minus G is compact.
So X minus G is compact. Thank you so much. Yeah, because closed subsets of compact sets are compact. X minus G is closed in X and hence compact. So you have a compact subset of X. Yeah. And now I am going to apply the continuous function f to it, right? A continuous function takes compact sets to compact sets. It follows that if I look at the set this, yeah, so what am I doing? I am looking at the complement of G, applying F. Now this is going to be compact in Y, right? Why? Because F is continuous and the complement of G is compact, and a continuous function always takes compact sets to compact sets. Is that okay?
Yes, ma'am.
Yes? Is everybody with me up till this point? Right? Now, this set, the image of the complement of G under F is compact, and hence, here's the next statement, and hence closed in Y. Why is this set closed? Because compact sets are always closed and bounded. Yeah, so all I'm using is that the image of the complement of G is compact and hence closed. So you might wonder, what am I trying to do and what is happening? Yeah. But anyways, let's see. Is everybody with me up till this point? Is that a yes with everybody present here? No, please
Yes, ma'am.
ask. Yeah, is that okay? All right. So what have we proved? You looked at the complement of G, push it forward by F, and I say that that set is compact and has closed in Y. That means that its complement is going to be open in Y. Yeah, what is the complement? Which means that I am looking at the complement of G, applying F, and then looking at its complement in Y. This set is open in Y, right? Because the complement of this set is closed in Y is what we just observed above. Is that okay? But again, using the fact that F is 1, 1 and on 2, what do we get? So let's remind ourselves that little f is a bijection. So that shows that this set, what this set, so you look at the complement of G, look at its image under F, that's a subset of Y, look at its complement in Y, this is exactly f of G. And hence we are done.
Ma'am, can you please elaborate the last point about how it came out to be FG? using the fact that it's a
Okay.
bijection.
See, this is very simple set theory. So what is that you're doing? I am looking at, so G is a subset of X, so is the complement of G. Yeah, so complement of G I'm writing as this. Yeah, so this is X minus G, this notation for X minus G. Now what am I doing? I am applying F here. So I get F of the complement of G, right? This is a subset of Y, and I am taking its complement in the set Y, right? Now this is exactly going to be F of G is what I'm claiming. Yeah, so you start with set theory, right? So you start with the point on the left hand side, and then so let me sort of do it here. Yeah. So so let's pick a point. Let me call it Y of F of G. Yeah. Then Y is, this is a plain set theory. Y is F of X. Yeah. And there is a unique such X, right? Saying that F is 1, 1, not 2, right? For some X in G. Right. Now, do you think you will be able to write little y as an element in here? Somebody wants to suggest something? Somebody wants to help me out with this? Okay, so let's just analyze sets if that makes you more comfortable, and this looks rather technical. See, let's look at these sets F and this set F, the image of G under the map F and the image of the complement of G under the map F, right? Now, these are two subsets of Y. Everybody agrees? Yes, because F is a map from X onto Y, right? Now, since F is 1, 1, this intersection is empty. There is no point which can be mapped to both of these sets simultaneously. There's no point of G and X minus G. Does everybody agree with me? This is the first thing that I have written in blue, is using the fact that F is 1, 1.
Yes, ma'am, it's clear.
Yes, because if there were a point in common, that would contradict the fact that F is 1, 1, right? Yeah. So this implies that, so I'll just note this, since this, hence this exactly implies that the image of G under the set F, under the map F, is contained in the complement of this set, isn't it? Because if this set does not intersect with F of the complement of G at all, it must lie in its complement, right? Is that okay? Is that okay with everybody?
Yes.
Yes. Now, how do we show the other way inclusion? So, how do we show this? that how do we show this inclusion? I like one of you to help me out here. Yeah, this is just set theory. See, again, you know, this is very simple using the fact that, so let me see. So let's start with the point of this set, right, of the left-hand side. Now, since f is onto, yeah, and little y is an element in y, there must exist a point x such that f is mapped, so f takes x to y. Is that correct? Yeah. Now,
Yes,
yeah, and since y is not in, does not come from this portion by assumption, where else can, what does it imply? You know, it is immediate that, you know, y belongs to f of g, right? Where else? That x belongs to g. Yeah. Now, since y does not belong to the image of the complement of G, it implies that the point X cannot belong to the complement of G because there is a unique such X, right? This is again unique point, yeah. So it is immediate that X belongs to G, yeah. So what have we done? Y, we have written Y equal to f of X, where X is a point of G, hence Y belongs to f of G, and we are done. Is that okay? Is that a yes with everybody? See, I
yes,
think
ma'am.
we have fixed it in all its gory details, right? Is that okay? Yeah?
Yes, ma'am.
Yeah? Okay, all right. Let me move on to something more interesting. Okay. So here is another interesting consequence. So, you know, so just a clarification on this side. Having fixed the proof for corollary 2, we can now talk about this theorem, which is very interesting in its own right and perhaps familiar. So let's see. Yeah. So let's consider a continuous function. Let f be a continuous function. Yeah. So x is a metric space and R is the real line here. And as before, unless otherwise stated, we are going to consider the real line with the Euclidean metric. So suppose that this is a continuous function. And suppose that X is compact. Yeah. So from a compact metric space X into R. Right? So what does it tell you? What does our earlier analysis tells us? It tells us that the image of this function, that is f of x, it's going to be compact subset of R, right? Because continuous sets take compact sets to compact sets, right? And we have a characterization of compact sets in the Euclidean metric, right? What are those? Those are, what are compact sets in the Euclidean metric?
Finite intervals.
Sorry?
Finite closed intervals.
Not finite. See, can't you have so finite? I agree is compact, but are those all?
Okay, sorry, bounded and closed.
Bounded and closed. But do you already need intervals? Is it necessary that it's an interval? For example, let's recall. We proved it rigorously in class, right? I'm writing something in blue ink. Right? So you look at this set 1 by n, as little n varies over the set of natural numbers, union singleton 0. Right? This is certainly not an interval, right? Is this an interval? This is not an interval, right? But this is compact. So what are compact sets in Euclidean metric? What are all compact subsets of in the Euclidean metric? What are compact subsets on R? I think it's time for a quiz. Yeah. Okay. Anyways, let me go ahead. So the statement of the theorem is, yet I have a continuous function from a compact metric space X into the real line. Then the claim is that then there are points P, Q in X satisfying So what are P and Q doing? P and Q are points where the extremal values of F are realized. The maximum and the minimum of F are realized. If you have a continuous function from a compact metric space into R. Right? So f of x, which is a subset of R, right? So I'm now taking the supremum over f of x. It is saying that there is some point P where the supremum is realized. Is that okay? And likewise, f of x, the infimum of f of x is realized. Yeah, so it's actually maximum and minimum. Does everybody follow what is this theorem saying? See, this is sort of a finer version of something that perhaps you are already familiar with. I would just list it downstairs here, which is the extreme value theorem. What is the extreme value theorem? So instead of any compact metric space, I will look at f as a function from closed and bounded interval AB. Yeah. So this is an example of a compact set on the real line. Yeah. So let f be a function defined on closed and bounded interval AB, real valued function, and suppose that f is continuous. So f is a continuous function So instead of an arbitrary compact metric space, I am now looking at function defined on a closed and bounded interval in R. Right? So these are compact sets in R. This is what we have already done. Then this theorem that I've stated above is exactly saying that then F is bounded on a closed interval AB, which means that the supremum and the infimum of F exist. Right? And moreover, F attains its bounds. Yeah, that means that there are points let me use the same as upstairs in the interval AB such that so the supremum of F is realized at so maybe I'll write it like this if that looks more transparent. So the supremum of F is realized at the point P and the infimum of F is realized at the point Q. So have you seen extreme value theorem some point of time before? It doesn't matter if you have not seen it, but anyways, I thought it might be a good idea to tell you what it means in the real line. But so this is a very simple corollary of the statement of the theorem that we are interested in. So over here we have a general metric space which is compact by assumption. Yeah. So does everybody follow the statement of this theorem? And what is it saying? Is everybody with me?
Yes, ma'am.
Yes. Okay. All right. So let's just quickly see the proof of this theorem before we work out some examples. So let's see. So proof of the theorem. Which theorem? So let me give it a name. Theorem 1. So this is theorem 1, right? So again, I'm going to ask the same question. So given F, a continuous function from a compact metric space, we know that a continuous function takes compact sets to compact sets. So F of X is going to be a compact subset of R, right? Now, what can you say about compact subsets of R? What more can you say about compact subset of R? Since F is continuous, and X is compact, So what more can we say about f of x? How do we characterize compactness on the real line with the Euclidean metric?
Ma'am, it is closed and bounded.
It is closed and bounded. Thank you so much. Yeah. Okay. So compactness of f of x implies that this is a closed and bounded subset of R. Right? So the first part is done, that f is actually bounded. Right? Now, so now you look at what is that we are trying to do. Yeah, we have to find points P and Q so that supremum of infimum are realized. But wait a minute, even before, one should say that why do the supremum and infimum exist? Yeah. So so this is just on the side. I'm looking at the set f of x. Right? This is always non-empty. Correct? Now, saying that f of x is bounded, now I have a non-empty bounded subset of R. So the completeness property of R tells me that the supremum and infimum of this set exist. Is that okay?
Yes, ma'am.
Yes, so I'm going to note that down. That's the first observation. Even before I say that the supremum and infimum are realized, the first claim is that they exist. Yeah. And for that, you need the fact that f of x is bounded. Yeah? It follows from the completeness property of R that supremum of f of x and the infimum of f of x exist in R, right? They exist, right? And top of it, so this is by the completeness property. Furthermore, see, in general, the supremum of a set may or may not belong to that set. Yeah, which means that the supremum of f of x may not belong to that set. But here I claim that the supremum of f of x belongs to the set f of x. Why is that the case? Why is that the case in this case? See, for example, if I look at the set E as 1 by n,
Ma'am, because it is closed.
because it is closed. Yeah. So since the set, yeah, thank you so much. I'll just write it down here. So since f of x is closed, it would contain all of its limit points, and the supremum f of x is actually a limit point. Yeah, there is a sequence of points from f of x converging to supremum of f of x. It follows that the supremum of f of x in fact belongs to f of x, and similarly the same statement is true for the infimum also. Yeah. Yeah, this is exactly saying that there are points P and Q in X such that the supremum of f of x is realized at the point f of p. Yeah? So it is attained at the point p. And likewise, a similar statement is true for the infimum. Is that okay?
Yes, ma'am.
Yes? Okay, excellent. Yeah, so let's do a couple of examples. So let's look at examples. So let's look at the first example. So let's look at f defined on open interval 0, 1 to open interval 0, 1 by setting so this is the identity map on the open interval. Yes. So f of x is x for each point in the open interval 0, 1. Right? Okay. So then clearly f is continuous, right? In this example. There is no ambiguity about that. So then f is continuous in this example. And then, let's look at the image f of 0, 1. Yeah, so that's this set. And so what would be the, so this image in this example is actually the open interval 0, 1 itself, correct? Which means that if I want to take the supremum, what is the supremum of open interval 0, 1? What is the supremum of open interval 0, 1?
1.
1, correct? Now again, the image in this example can be completely explicitly computed, which means that if I want to take the infimum, so that's the infimum of 0, 1. So what is the infimum of the points 0 and 1? Sorry, infimum of the open interval 0, 1?
0.
0, right? Now, evidently, there are no points P, Q in open interval 0, 1 satisfying what? Satisfying either FP is 1 or so while the supremum of f of 0, 1, yeah, the supremum of the image of f, the range of f is 1 and the infimum is 0, these cannot be realized at any point in the domain by the function f, correct? Is that okay? There is no point P in the interval 0, 1 such that it is mapped to 1 yeah, by f, and there is likewise there is no point in open interval 0, 1 which is taken to 0 by the map f, right? So what is the issue here? What does our theorem say? Our theorem says that the supremum and infimum are always realized. So what is the issue here?
Ma'am, X is not compact.
X is not compact, yeah. So this example shows that the compactness of X is essential here as far as this theorem is concerned. Yeah, thank you so much. I'll just write that down. So you cannot compromise on the compactness of X. Compactness of X is essential in the statement of theorem 1. Right. Anyways, yeah. So a couple of more examples, yeah, to highlight this fact. Right. So what is it saying? It is saying that the theorem says that the image is the range set is bounded, and moreover the maximum and the minimum. Yeah. So in this case, the supremum and infimum are maximum minimum. Yeah. Saying that they are maximum minimum means that they are realized at some point. Okay. Yeah, so for example, if you look at another example, you look at the map from the real line into itself. And let me define it by setting f of x is 1 plus x square, the reciprocal of this. Right? This clearly, you can sort of do some work that here that f is continuous in this example. Is f bounded here? Is f bounded?
No, ma'am.
So why is f not bounded in this example?
Ma'am, because if x takes a value close to 0, then the value of fx rises to infinity. And
even if x is 0, then f is 1, no?
oh, okay,
There's no
sorry.
problem, right? There's no
Yes.
problem, right?
Yeah.
In fact, I would like to make the claim that f is bounded, isn't it? The first is that it's always positive, isn't it? And what is an upper bound for this? So the denominator is always at least 1, so which means that the reciprocal is at most 1 for all x in R. Is that the case?
Yes, ma'am.
Is that correct? F is bounded, isn't it? Is that correct? Everybody with me up till this point?
Yes, ma'am.
Yes. But so here let's look at this example. I have a continuous and bounded function on the real line, but f does not attain its bounds. Well, does it? Is that correct? Yeah. And again, R is not compact in this example. Is that okay?
Yes.
Yeah. So something very, very peculiar and follows thanks to compactness assumption. In here, right? And we saw an example to substantiate the claim that the compactness assumption here cannot be dropped. Okay. Okay. So let me just revisit the concept of continuity here. So recall, are there any questions in what we discussed so far? Please ask if there are. Yeah. So meanwhile, I'm just recalling the definition of continuity between two metric spaces. So if a function between two metric spaces is continuous on x if the following happens. Yeah, if it's continuous at each point of x, which means that at each point x naught and for every positive epsilon, there is a delta such that whenever x is in delta neighborhood of the point x naught, which means that the distance between x and x naught is at most delta, then f of x is within the prescribed epsilon neighborhood of the point f of x naught, yeah, which means that the distance between f of x and f of x naught is at most epsilon, yeah. So the delta that we have to produce corresponding to epsilon in general depends on epsilon as well as x naught, right? Is that okay? Everybody remembers this definition?
Yes, ma'am.
Yes? Okay. So what I want to emphasize here is that even for a fixed epsilon, so you keep the epsilon fixed, but you vary the point x naught, different x naughts might require different delta. Yeah, let me try to give you an example to convince this. Yeah, so let's look at an example. Let's work out that a function is continuous using the epsilon delta definition. We haven't done that so far, so it is anyways a good idea. So let's look at let f from the open interval 0 to infinity to open interval 0 to infinity be given by. So I have to tell you what happens to x. Yeah, where does f send it to? So I'm going to send it to the reciprocal of x. Yeah, so this is a well-defined map. There's no problem. We are away from the origin, right? Okay. So let's fix a point. So let's fix a point x naught and try to show that using the epsilon delta definition of continuity that f is continuous at that point x naught, right? So let's fix a point x naught and let's fix some positive epsilon. What are we required to do? We are required to find a delta such that whenever we are in delta neighborhood of x naught, there must be, then f must take it into epsilon neighborhood of f of x naught, right? So let's just recall that we will show that there is a delta positive such that if x is in a delta neighborhood of x naught, which means the following, then f takes it to epsilon neighborhood of f of x naught, right? Right? And we are given here f explicitly, so I am going to write that down. Yeah. So everybody is with me up till this point? Is that a yes for everybody present here?
Yes, ma'am.
So let's look at what is that we have. So let's consider the difference f of x minus f of x naught, right? By definition, it is reciprocal of x minus reciprocal of x naught, which is the absolute value of x and x naught. And downstairs we have this. I can forget about the absolute value in the denominator because everything is positive here, right? Now, how do we choose delta in this example here? How do we choose delta? Would somebody like to help me out? Okay. I don't get any response. So let's see. So let's look at what I have. See, the difference f of x minus f of x naught turns out to be this quantity on the right, the absolute value of x minus x naught, which is at most delta. The numerator here is bounded by delta, there's no problem. See, denominator here also, x naught is harmless. What is that we have to do? We have to get a bound for this little x which is in the denominator. Is that correct? We have to get rid of this little x here in the denominator. Now, how do we do this? All we know is that x lies in delta neighborhood of the point x naught. Now, what delta is something that we have to choose. Yeah. So, what is that I have? So let me, I'm just trying to sort of scribble here as to what is that I should do so that I am in safe hands. So, let's see. So, if x comes from delta neighborhood of x naught here, right? So what does it mean? Let's just unwind this inequality. This means that x is in the interval x naught minus delta, x naught plus delta. Yeah, which means that I have the reciprocal of x here, right? Where do I have the reciprocal of x? I'm looking at the reciprocal of x here. I need an upper bound on the reciprocal of x. Now, an upper bound on the reciprocal of x amounts to a lower bound on little x. Now, a lower bound on little x is here. A lower bound on little x is bounded below by x naught minus delta. Yeah. Now, somebody wants to tell me what should I choose delta to be? Yeah, please go ahead. Go ahead. Somebody wants to say something? Okay. All right. So let me see. So I suggest that let's take. I suggest that let's take delta to be less than x naught by 2. See, why do I do this? If I take delta to be less than x naught by 2, yeah, so I will get this here. I have an inequality here, this. Then what happens? Then x would lie between x naught plus delta, which is 3x naught by 2, and x would be at least as big as x naught minus x naught by 2, yeah, which means this is x naught by 2. Is that correct? So then if I look at this difference of f of x and f of x naught, that is, by definition 1 by x minus 1 by x naught. Yeah, so this is x minus x naught by x naught. The numerator is bounded by delta. The denominator is x naught. Is 1 by x. Now I will bound by 2 by x naught. Is this okay with everybody? Is everybody with me up till this point?
Yes, ma'am.
Yes. Now what is my goal? See, remember, what is my goal? I have a fixed epsilon, right? I have So what is this saying? This is saying that, what is given to me is epsilon. So so this is my point fx naught, and epsilon is given to me, yeah, which means this interval around fx naught is given to me. What is that I have to find? Delta is something that I have to find. So I have given this delta. Now, how should I choose delta such that what happens? Such that whenever I pick any point in this delta neighborhood around the point x naught, f of that point, the image must be in this prescribed neighborhood of the point f of x naught. That's what continuity says. Now, what is that I want? I want this to be less than epsilon. So, which means that delta should be at most epsilon x naught square by 2. Is that okay? So, what should be my delta? Now, can somebody help me? So I want delta to satisfy two inequalities simultaneously. Which one? Delta should be less than x naught by 2, which is here, and delta should also satisfy less than epsilon x naught square by 2. So if I want both of them to hold 2 simultaneously, what should I take delta to be?
The positive square root of their product? I don't know. It's just a guess.
See, what will I achieve if I take a positive square root of their product? Where is that thought coming from? I'm just trying to understand. You may be right.
Ma'am, just because of the fact that then delta would accommodate both the conditions, I guess.
But one way to fix that is you take delta to be the minimum of these two quantities. No, that is also a way to go about it. So you define delta to be the minimum of these two quantities. Isn't it? Is that correct? If you define delta to be minimum of these two quantities, then also both these inequalities hold true. Is that correct?
Yes, ma'am.
Yes. See, all this what I have written is just to sort of highlight how to get to this. So if somebody asks you a question that, prove that this function is continuous using the epsilon delta definition, see, all that I have written here, this thing. This is something that is all that goes on in your mind. Yeah, all of this. This is not required. See, if you look at usual text, what it would be written is, you would be written as fix x naught, a point in 0 to infinity, and fix epsilon positive. We are required to show that if x is in delta neighborhood of x naught, then f of x is in epsilon neighborhood of x naught, a of fx naught. Let's pick delta to be minimum of these two. All I'm trying to do is, by this analysis, I am trying to show you where does this come from. So if you define delta like this, then if x is in delta neighborhood of x naught, then f of x is in delta neighborhood, is in epsilon neighborhood of f of x naught. And hence, f is continuous. Is this okay with everybody present here? Any questions, please ask. So do I assume this is okay with everybody present here? Okay. See, here's something that I wanted to say. See, there's no uniqueness to the choice of this delta. Yeah. See, why did I take x naught to, delta to be less than x naught by 2? I can take it to be less than, for example, x naught by 3, and similar thing would work. There's no uniqueness here. This is one such delta which does the job. Right? You may choose to do something else. There's a lot of flexibility here. But you should know how to sort of play around, how to use that flexibility. The point that I wanted to emphasize is that even for a fixed different x naughts might require different delta. See, for example, in this, the delta that we have produced depends on both epsilon as the point x naught. Yeah? So if we wish to consider all the points x naught in the entire interval where f is defined, which means that if we wish to consider all x naughts in the interval 0 to infinity, and you want to choose one delta which will work for all the point x naught, is that possible? Yeah, so what is that I am trying to say? I am trying to say that if we wish, so if we want to consider all the points in the domain of definition of f, this formulae means this formulae for delta does not lead to one value delta that will work simultaneously for all x naught positive. So all I'm trying to say is that suppose now I give you, so this is some point x naught, right? We show that f is continuous at the point x naught. Now if I pick, so let's say x naught is 1. Now if I pick some other point, let me pick y naught is equal to 30. Yeah, and I ask you, show that f is continuous, find me a delta, right? The same delta will not work there, right? If delta 1 works for x naught equal to 1, then delta 1 may not work for y naught equal to 30. Is that okay? At least going by this formula, right? So this is what I'm trying to say. There is not a single value of delta that will work for all the x naughts, as x naught vary over the interval 0 to infinity. Why is that the case? Because if I take the infimum of these delta as x naught goes to 0, that infimum is 0 in this case, right? So delta here depends on x naught as well as epsilon. And there's no positive delta that will work simultaneously for all of these x naught. At least this formula says so. Is that okay? Does this make sense to you? Whatever I'm trying to say? Is everybody with me?
Yes, ma'am.
Yes. So there is not one single delta that will work as far as definition of continuity of f is concerned using this formula for all the points x naught in the definition of f, right? Okay. So this brings us to the following definition, which is of uniform continuity. Yeah. So let me write down what is it I want to say. So here's the definition. Suppose that f from x to y is a function, yeah, between two matrix spaces x and y. Okay, we say that f is uniformly continuous on x. F is said to be or defined to be uniformly continuous on x if the following is true. If for every epsilon positive, there is a delta such that for all the points x and p in x, f of x is in the prescribed epsilon neighborhood of the point P whenever x and P are in delta neighborhood of each other. See, what is the difference here from continuity? So let's note this down. Yeah, so x is here and y is here. You have a function, right? Now, what is that you are saying? You are saying no matter where you are in x, yeah, no matter. Now you give me an epsilon and you fix a point in y, yeah, f of p, and you fix an epsilon neighborhood around that point. Right? There is a delta such that whenever you are in this delta neighborhood of the point P, f takes you into an epsilon neighborhood of the point P, of f of P, right? Now, the point here is, how is uniform continuity different from continuity? The same delta works for all the points in x and p. So the delta here depends only on epsilon and not at the point where it is chosen. This is much in contrast to the example that we considered. Yeah, in the function, you know, for example, this function. Let me just highlight this. So, for example, the function that we just considered, you know, f of x equal to 1 by x. This function is certainly continuous on open interval 0 to 1. That's what we showed, right? Corresponding to each epsilon, we demonstrated that there is a delta such that whenever I am in delta neighborhood of a point x naught, then f takes me to an epsilon neighborhood of the point f of x naught. But here is a caveat. But if we want what? If we want that the distance between f of x and f of p, which means that the following, yeah, this should be less than epsilon whenever the distance between p and x as at most delta this cannot happen. This cannot happen. You know, the delta cannot be chosen independent of the point P because x would be arbitrary close, can be taken arbitrary close to 0, and so 1 by x could be arbitrarily large, and that's what the problem is. Yes. Now, for example, I'll give you an example of, you know, this was an example of a function which is not uniformly continuous. I'll give you an example of a function which is uniformly continuous. Yeah, so that will sort of clarify things. So let's look at f, again defined on open interval 0, 1 into r. Let me define f to be 2x, for example, something very simple, right? Now I claim that this function is uniformly continuous. Why? Because let's look at this. Yeah, so you fix epsilon positive, and let's look at f of x minus y. Yeah, so for x, y in the interval 0, 1, let's look at this. So this is by definition 2x minus 2y is 2 times x minus y, right? Now, how should I choose my delta in this case? Can somebody help me out here? How should I choose my delta?
Epsilon by 2.
You choose delta to be epsilon by 2. Yeah, so let me write that down. Thank you very much. Take delta to be strictly less than epsilon by 2. Yeah, I am not taking it to be equal to epsilon by 2. Let's take delta to be strictly less than epsilon by 2. And then if x and y are at most delta distance apart, then fx and fy will satisfy 2 delta is at most epsilon, right? So please note that much in contrast to the previous example, over here the delta depends only to dependent on epsilon. The same delta works no matter where I am on the interval 0, 1. Yeah? So hence the function f is uniformly continuous in this example. Is that okay? So uniform continuity is a property of a function on a set. However, continuity can be defined at a point, right? It doesn't make sense to say that f is uniformly continuous at a point. Yeah, that doesn't make sense. Uniform continuity is a property of a function on a set. So for each epsilon positive, there is one single delta that will do for all the points of x. That is what uniform continuity is all about.